Hi everyone, so today we'll be discussing chapter 2, which is on capacitors. So this will be on section 1, capacitor and capacitance. But before we really go into details on the idea of capacitors and capacitance, we will get a bit, let's jump out a bit and let's talk about electrical components in general. So we will try to talk about, like, if we have any kind of electrical components, let's say we have a buzzer or we have a light bulb, or we have a motor. Okay, in general, how do we operate such an electrical component? How do we provide the energy for them to be operated? Okay, so once we have the idea that how an electrical component can be operated, we will try to think about how do we make that situation possible for these electrical components to function. So we'll think about how do we get charges to have electric potential energy in the first place. Okay, we know that we'll be using electric potential energy to operate an electrical component. So we'll be discussing how do we get the charges to have the electric potential energy in the first place. So once they possess the electric potential energy with the help of the battery, we will be using the electric potential energy to operate the electrical component. So you get a rough idea of how a modern day electric circuit, generally how does it work. So once we have an idea of this, we will go more specifically into our topic for today, which is of capacitor. So we'll be discussing the purpose of capacitor, and the purpose of capacitor later we'll see is to store electric potential energy. Okay, then because the purpose of this component is to store electric potential energy, we need to know how do we charge the potential energy into the capacitor, and that is by battery. And how do we discharge it? Is by letting the charge flowing out from the capacitor when you are not installing it to the battery. So we learn how to charge a capacitor and also discharge a capacitor. Okay, then we'll see if we have such a component that can be charged and discharged over a certain period of time, what can these kind of components do? Okay, we'll see that it can be used as a short-term power source and other functions as well. And then we'll enter some real mathematical details and talk about how do we quantify the ability of a capacitor to store charge and energy. So how do we store charge? How do we store energy? We can quantify the ability using the quantity capacitance, where capacitance is equals to the charge stored divided by the potential difference across the capacitor plates. Okay, so that's a lot to cover within one video, so let's get right into it. So how do we operate a load? So a load is something that uses electrical energy. So any kind of components that you have in the circuit that consumes energy, okay, or use energy, we call it as a load. So we can think of it as resistors. Let's say resistors, you take out the energy from the charges that pass through it. You also have light bulbs, you also have buzzer. This kind of components, their purpose is to use the energy, the electrical energy, to perform some kind of function. So in this case, the light bulb will be to light up, the buzzer will be to produce sound, right? Okay, so these are the purpose of load. So to operate these electrical components, we need to supply electrical energy in order for it to work. So you know that they need the energy, so we need to supply them with the energy. So let's look at the analogy of a water wheel to understand how do we operate a load. Okay, so this is a medieval times water wheel, or you can probably see in these days as well. I think they use it for agricultural purposes as well. Okay, so I'll draw a cartoon of it to show how does a water wheel works. Okay, so you can see that this is a water wheel. It needs to be spun so that it can the rotation here will be converted to using a dynamo. Maybe the rotation here, the kinetic energy here, can be converted into electrical energy that can be used. Okay, or it can be used to rotate a turbine, then it transforms gravitational potential energy to kinetic energy. Okay, there's some form of transition of energy over here. Okay, but how do we make it work? Okay, water loses gravitational potential energy as it moves from higher to lower ground. So in this situation, you can see that there's water flowing out from this pipe, flowing from a higher ground to a lower ground. The loss of gravitational potential energy is transferred to the water wheel to rotate it. Thus, useful work is done. Okay, so when your water flows from a higher ground to a lower ground, what happens is there will be a loss of gravitational potential energy, right? So the loss of gravitational potential energy is not that the energy is destroyed or what. It is somehow being transformed okay, into kinetic energy for the water to move. Okay, but when the water moves, it hits onto the water wheel. So therefore, this energy gets transferred to the water wheel and in turn make the water wheels rotate. So this is how you get the water to pass its energy, which is initially gravitational potential energy. You transform it into the kinetic energy of the water to flow. Then you pass that energy to the water wheel, making the water wheel to rotate. Okay, so this is a simple example of how we take the potential energy of the water and transfer it to the water wheel, in this case to make it rotate. So you can think of the water wheel in this situation to be similar like the load, okay, because their function is to consume the energy from the water that flows through it. It consumes the energy in order to rotate, to perform some kind of useful work over here. Okay, so we know that higher ground here means higher potential. We learned about the concept of electric potential. So in this case, this one, higher ground means higher gravitational potential. Lower ground means lower gravitational potential. So that's the idea of a water wheel. Now let's look at the circuit. Okay, so here I have a battery, ever ready, not the ever ready that you know of. Okay, you have a battery here with a positive terminal and a negative terminal, and you connect this battery here to a light bulb. Okay, so what can we know about this simple situation here? Electric charges lose electric potential energy as it moves from the positive terminal to the negative terminal. Try to see that this sentence here actually has the same structure as the first sentence over here, where it says water loses gravitational potential energy. Here it's charges loses electric potential energy as it moves from a higher ground to a lower ground, but for charges it moves from the positive terminal to the negative terminal. So you can think of this situation like this. You can think of the positive terminal here as a higher ground. In this situation, think of it as a higher ground. Then you have positive charges, these charges here, flowing from higher ground to the lower ground, which is a negative terminal over here. Okay, you know that charges, okay, which are positive, okay, these charges that are flowing is positive. Technically, they will get attracted to the negative terminal because positive negative attract, so they will naturally want to move from this higher electric potential region. They'll naturally flow to the negative electric potential at the lower electric potential region, which is the negative terminal over here. Okay, it flows naturally. You do not need any kind of external source of energy for it to happen. Things just fall, okay? Things naturally fall from higher ground to lower ground. You don't need any hand to push the water to a lower ground, right? Same idea over here. These positive charges don't need any kind of external kind of motivation to push the charges from a higher electric potential region to a lower electric potential region. It happens automatically. Okay, so when it moves to the negative terminal, you lose electric potential energy. So what does it lose to become? Again, it is not destroyed. The energy is not destroyed. It is merely being converted into some other form. That loss of electric potential energy is actually transferred to the light bulb to light it up. Thus, useful work is done. So what has been lost by the charges when it moved to the negative terminal will actually be transferred to the light bulb, and be transferred into the light bulb, then it will be converted into light energy. So in that case, you can see the light bulb lights up, which is a form of useful work. Okay, so every time you look at the circuit, I would like you to try to think about it. Who is providing the energy? In this case, it's the battery that is providing the energy. Then after that, battery pass energy to the charges. Then when the charges flow through the electrical component, in this case a light bulb, when it flows through a light bulb, it will pass the energy. It will lose energy, and the energy gets transferred to the light bulb to light up the light bulb. Okay, so that's how I think it's an exchange of energy from one object to the charges, from the battery to the charges, then from the charges to the light bulb. It's a passing of energy that we are talking about here. Okay, so there's something I want you to take note over here, which is electric charge in the electric circuit means positive charge. So conventionally, when we talk about current or we talk about charges flowing in the circuit, we are referring to the positive charge that is flowing. Okay, but that doesn't mean that the protons are moving in the circuit. In fact, in reality, it's the electrons that are moving in reverse direction from low potential to high potential. Okay, what does it mean? Conventionally, okay, on everyday physics language, if it says that charges flow from positive terminal to negative terminal, or current flows from positive terminal to negative terminal, we are thinking of a positive charges that are moving from the positive terminal over here flow towards the negative terminal. But that positive charges, it's just a merely a imaginative kind of positive charge, I would say so. Okay, because what really happened is, what exactly happens inside the wire is not that the protons, which are the positive charge that are moving from positive terminal to negative terminal, it's not the protons that is moving actually. If you observe the wire inside, what actually happened is the electrons that are moving, okay, as you can see in purple here, it is the electrons that are moving from the negative terminal to the positive terminal in the reverse direction. So this is the reality. What is happening? It's the electrons that are moving from negative terminal to the positive terminal. And this is from the low electric potential region, the negative terminal, to the high electric potential region, which is the positive terminal. Okay, however, the problem is we are more used to seeing things gain potential energy when move from low potential to high potential. Okay, we always say a block, when it moves from lower ground to higher ground, it gains gravitational potential energy. We are so used to that. If you go higher, you gain potential energy. If you get to a lower ground, you lose potential energy. That's what we are used to in our daily life really. So what electrons do here, it loses energy when it goes from low to high, which is very counterintuitive. Okay, let me clarify things a bit. Okay, we are very used to saying that gain energy is we go from low to high, lower ground to higher ground means we gain energy. But we lose potential energy when we go from high to low. Very easily imagine, if you make something fall to the ground, the process of it falling to the ground, we lose potential energy. So that's what we are used to. Okay, so what we'll do, we will stick to electric charge, which is the reverse of electrons in our discussion of electric circuit. Okay, so what does it actually mean? Okay, these electrons, they don't follow the way our daily life works. Daily life, usually we say go from high to low, you lose energy. Go from low to high, you gain energy. But let's look at this situation. Electron, it will flow naturally this way. So flow naturally this way, we know that object, they flow naturally from high ground to low ground. Water flows naturally from high ground to low ground. But you see here, these electrons here, they are flowing from low to high, which is the reverse of what we usually think, the reverse of our commonly thought kind of direction. Okay, we usually think object, they will flow naturally from high to low, but this one, electrons flow naturally from low to high, which is the reverse direction. Then we see, okay, electron, when they pass through the light bulb from low to high, they will pass through the light bulb, then it will lose energy to pass it to the light bulb. That's what actually happens in the circuit. The electrons carrying a lot of energy coming out from the low electric potential region, pass through the light bulb, pass the energy to the light bulb, then it exits the light bulb with little energy left. Okay, so the process of going from low to high actually loses energy for the electrons. The electrons lose energy when it goes from low to high. Does it match with what we know about our real life? Real life, for us to lose energy is if we fall, if we drop an object, it goes from higher ground to lower ground, it will lose gravitational potential energy. But here we see electrons, it lose energy when it goes from low to high, which is again reverse of what we usually perceive of our daily life. So because it's so unnatural to think about it in a reverse way, what we do is we won't talk about current, or we won't talk about charges as the actual electrons. Instead, we will think about the charges to be something like a reverse of an electron, an imaginary opposite of an electron that moves from high electric potential to low electric potential. we think of a character which is the opposite of electron. And now things will make more sense because the opposite electrons will move in opposite direction, which is from high to low. So when it moves from high to low, follow the pink arrow over here, you pass the energy to the light bulb. So go from high to low, you lose energy. So lose energy, you pass it to the light bulb. So everything makes more sense with our daily life. That's why we choose not to explain electric circuit in electrons because it's counterintuitive. What do? We explain it in terms of the opposite of electrons or the reverse of electrons, which we just call it as electric charge. So this electric charge will move from high potential to low potential. And in the following discussion, we won't be talking about electrons anymore. When we talk about charges flowing from where to where, we are always referring to that imaginative positive charge that we are talking about over here. So no more mentions regarding the electron from further on. Okay, of course, if you choose to stick to electron for the whole story, it's still okay. But you have to squeeze your brain a bit to think everything in a reverse way. Go from low to high is actually a loss of energy. Go from high to low is actually a gain of energy. You have to reverse your daily life kind of common sense in doing so. So we prefer to stick to positive charge, and that's how we do it further down this class. Okay. So how do we get charges to have electric potential energy in the first place? Okay. In other words, okay, you want the charges to have potential energy. Is imagine you have a ball. If you want it to have gravitational potential energy, you have to bring it to a higher ground, right? So if you look at a water wheel, water naturally flows from higher ground to lower ground. So if you want it to have gravitational potential energy, you have to put the water at the higher ground in the first place, because higher ground means higher potential. Higher potential means, but if your water is at the higher ground, you have more gravitational potential energy. So you want it to have more gravitational potential energy in the first place, so that it can pass the energy to the water wheel for the water wheel to rotate. So that's the idea. So our question will be, how do we put water at the higher ground so that it can be used to power the water wheel, to rotate the water wheel? So how do we bring it up? You need some kind of a pump, or you need some kind of a storage system. So logically think about it. You want to bring the water to a higher ground. It's something that is difficult. It's something that requires effort. So if it requires effort, you can think of it as something like a pump, which you need to run on electric in order to bring the water to a higher ground. Or you need some kind of nature's effort, which is something like a rain, maybe rain to shift the water to higher ground. So rain is the earth effort in bringing the water from lower ground to higher ground. You evaporate the water using heat, bring it out as cloud, and shift it to a higher ground, then you let the raindrops fall. So it's earth's effort, earth putting in the effort to shift the water to higher ground. That process itself requires effort. That's the main thing that we want to talk about. So you need some kind of pump, or you need some kind of storage system. Okay, so here I have a few examples. So if it's a pump, you can imagine that there's a pump represented by a cross over here, a circle and a cross over here. So you bring water from the lower ground, you use electrical energy, you pump the water up to a higher ground. So this is how you can bring the water to a higher ground using water pump. But you need to know that this process requires effort. So because it requires effort, you need to draw the energy from somewhere. You need to bring in the energy from somewhere. Where do you bring the energy from? You use electrical energy. So this is what you do in the daily life to bring water to a higher ground. Okay, another way of doing bringing water to a higher ground is use storage system. Okay, or as we call it in Malaysia, the tangki. Okay, so how does tangki works? Well, you still need a pump actually. You need a pump to draw water from the lower ground. You pump it to the higher ground. But what's good about a storage system or tangki here is that you can store water here temporarily. Okay, you can stop the water from flowing out. You close the pipe over it, you close the tap over here. So what happens is water is being stored in the higher ground temporarily. Once you open the tap, the water will flow out. But what you can do using a storage system is you can bring the water to a higher ground and you store it. That's the beauty of this kind of system. You are able to store it. If you just have a water pump, the water will shift to higher ground, but you continuously flow to a lower ground. You are not able to store it for a certain amount of time up there. Okay, but if you have tangki or you have a storage system, you can bring the water to a higher ground and you can store it there first, so it can be used at a later time. Okay, so the process of us bringing the water up to into the system to be stored is the process of charging. Okay, you can think of it as pumping the water from the lower ground into the tangki is the process of us charging the tangki. Okay, charging the storage system. Then when you open the tap, letting the water flow out from the tangki to a lower ground while passing through the water wheel, that process itself, it's water flowing out to rotate the water wheel. So that process itself, you can think of it as discharging, where you have charges flowing out, okay, used to do useful on a certain load in this case. Okay, so I will do a situation. How can we think of this pump system here? How does it relate to an electrical circuit? If it's a storage system, how can we think of it in the electrical circuit sense? Okay, so if it's a pump, okay, where you have a pump bringing it to higher ground, you can think of the pump similar to a battery. Okay, so a battery actually functions as similar like a pump, or it's actually pump. Actually, a battery is a pump, because what does it do? It brings the charges that has no energy anymore, the positive charges that we have at the low electric potential region. Okay, these are like near the ground already, so these charges, they do not have electric potential energy left because they are at the ground already. So what do? We install a battery over here, and what does the battery do? The battery will use the chemical energy inside the battery to shift the charges from places which has low electric potential to a region with high electric potential. So you can think of it similar to like the similar like a pump. Okay, you bring it from somewhere which is lower ground, you bring it somewhere to a higher ground. This process here requires effort, so it requires energy. Where do you draw the energy from? You draw the energy from the chemical energy of the battery itself. Okay, so once you draw the charges to the higher electric potential region, now over here they possess electric potential energy already. Okay, before that it has little to no potential energy at the low electric potential region, but once the battery provides the chemical energy to shift the charges to the high electric potential region, what happens when it exits the battery? It exits a battery with a lot of electric potential energy. So once you have a lot of electric potential energy, it will flow through the current, pass the energy to the light bulb, making the light bulb works. And once it passes energy to the light bulb, you'll be left with little to no electric potential energy, and you return back to the low electric potential region. Okay, so you can look at these two diagrams and try to draw a similarity between the two. So the battery will be the pump in this case, whereas the water wheel here will be the light bulb in this case. So the water is the one that acts as the tool to transfer the energy from the battery to the water wheel. The battery provide energy, then the water wheel receive the energy. But who's the one bringing the energy along? It's the water that carries the energy. Okay, so here battery is the provider of energy, it's the source of energy, whereas the light bulb here is the one that will consume the energy, or we will use the energy. But how does the energy get from the battery to the light bulb? Well, the charges are there to bring the energy from the battery to the light bulb for the light bulb to work. So that's how you can think about the situation. Okay, so we come back to the tangki system that we have earlier, this storage system, where you have water being pumped up and being stored in a tank. Okay, so in electrical circuit, how can you think of it? You can think of it low electric potential. Low electric potential is this region over here. You can think of here as the ground. So what happened is you can bring positive charges through the effort of this battery over here. You can bring the positive charges from low electric potential, you bring up to another plate of the capacitor. Okay, a capacitor has two plates. One of the plate will simulate the lower ground, okay, which is the ground over here, while another plate will simulate the higher ground over here. So if you bring water or you bring charges continuously from this one plate to the opposite plate, it's as if you are bringing water, shifting it up to the upper plate to be stored. So now you have more charges being stored in this upper plate over here. Okay, so once you feel like you have charged your capacitor enough, what you can do is you can just remove the battery. Then now the charges will still be stored in the capacitor, waiting for its time to be discharged. Okay, waiting for its time to discharge. So again, what happened? Let me edit a bit the diagram. I do not want I will edit it. We will not discuss electrons in this situation, so let me remove the negative one. Okay, so just focus on the positive charges. Okay, so in this case, what happened is your positive charge which was initially at the low electric, which was initially at this plate, will get shifted to another plate over here. Okay, when it gets shifted to another plate over here, this region here will be high electric potential, whereas this region here will be low electric potential. So slowly you create a potential difference across these two plates over here. Okay, so let's look at battery first. Battery, chemical energy of the battery is used to move the charge from region of low potential to region of high potential. Again, here is low potential. We use chemical energy to bring it to high electric potential. This direction of motion is not natural. As I say, to bring an object from lower ground to higher ground is not something natural. It requires effort. So it requires chemical energy of the battery to make it happen. So you need to draw energy from an external source, which is the chemical energy in this case. Okay, so for charging a capacitor, which is what happened in this diagram here, charges are shifted from region of low electric potential to region of high electric potential using battery to be stored. Okay, so when we bring charges using this battery here, when this battery provides energy to bring the charges from one plate to another plate, then here will slowly be the high electric potential region, whereas here it will be the low electric potential region. So this process is similar to us pumping water from the ground into the water tank. Okay, so as you bring more and more charges around, then you will create a positive plate around here, you create a negative plate around here. So now what happened? Electric potential energy is thus stored in the capacitor when you have a positive and a negative plate here. Okay, let's continue to look at the right hand side over here. What happened is I have already disconnected the battery from this circuit, and now I can say that the capacitor is charged. After I charge it, I remove the battery, so the charge still remains in the capacitor. But what happened is I connect this circuit here to a light bulb instead. So now when I connect it to a light bulb, charges that are stored at the region of high electric potential, charges that are initially stored just now over here, are provided with a path to move to the region of low electric potential. Now you can see that there's a path available for these positive charges, which was initially here, to flow to the region of low electric potential. Okay, so they are provided with a path to move to the region of low electric potential, which is the negative plate. So the charges will move from the positive plate over here and move to the negative plate. Okay, so charges will move naturally from region of high potential to low potential. So if a load is installed along the path, in this case we install a load along the path from high potential to low potential, so the electric potential energy will be used to operate the load. So what happens is the charges, when they pass through the light bulb, it will pass the electric potential energy that it initially have to the light bulb, and the light bulb who receives the energy will use the energy to operate the light bulb, in this case causing it to light up. So it is similar to us having water flowing out from the water tank, pass through the water wheel before reaching the ground. Okay, so it's similar to us having water flowing out. Okay, this water possess a lot of gravitational potential energy. They pass the gravitational potential energy to the water wheel by changing it into kinetic energy. Then now the energy can be used to do useful work, but the water that comes out from the water wheel has no longer that amount of gravitational potential energy anymore. So same idea over here. When you discharge, initially you have a lot of electric potential energy. You pass the energy to the light bulb, so you're left with little to zero potential energy when you come back to the negative plate. Okay, that's the idea of it. Okay, so what's the purpose of a capacitor? The purpose of a capacitor is to store charge. Okay, as you can see here, when we are charging it, you are bringing charges from one plate to another plate. Okay, so it will cause one plate to be positively charged, another plate to be negatively charged. So the purpose of capacitor is indeed to store charge, and when you store charge inside, you will be storing electric potential energy inside. Okay, so knowing that, what can a capacitor do? Well, the capacitor can act as a short-term power supply. Okay, just like Tanki. You cannot draw water out from a Tanki continuously and infinitely. Okay, once the water in the storage system runs out, then that's it. There's no more water inside the storage system. You have used up all the energy in the storage system. Similar idea here. This capacitor here, when you draw electric potential energy out from it, there's only a limited amount of the limited amount of electric potential energy stored in the capacitor. So once you use up the amount of energy that is stored inside the capacitor initially, well, that's it. There's no more energy left in the capacitor, then you have no longer a power supply. Okay, so the power supply is a short-term power supply. So traditionally, like in old times, capacitor was used in camera flash, because as you can see, if you have a flash camera, if you take a picture, the flash only happens for a very short amount of time. It flash, then that's it. Then it dims off, then that's it, no more. Okay, so a capacitor will be suitable in those kind of situations because the flash only happens within a short amount of time, and that's just a finite amount of energy that you need. You don't need to keep flashing continuously. That's not the purpose of the flash. Okay, it only flash for a short while. So after it flash, then you use up the energy, then you can charge back the capacitor, then you can get ready for another flash. But a single charge is for a single flash. You can think of it like that. Okay, another purpose is to stabilize a current. Okay, so you can think of it, the storage tank that you have in your house is for you to cater for a situation where there's a water cut. So let's say there's no water coming out from your Jabatan Bekalan Air in Malaysia, or there's no water coming out from your, what do you call that place? Water plant. Okay, I can't really remember. Water processing plant. Okay, there's no water coming out from it, so there's a water cut. So if there's a water cut, then it's good that you have a water tank because it serves as a temporary source, right? Okay, so it's a similar idea. So in your circuit, your battery doesn't always function optimally, or your power supply doesn't always function optimally. Occasionally there will be a situation where there's down in power supply. Okay, there's a bit of a dip in the power supply. So if there's a dip in power supply, then your capacitor will function to complement that dip in the power supply. Okay, when there's a drop in the amount of energy provided in the battery, then the capacitor will be there to cover up or to complement the amount of drop of energy that was provided by the battery. Okay, it doesn't exactly happen that way, but you can sort of think of it that way. Okay, so that's another purpose of a capacitor as well. Okay, so we have discussed a lot regarding the rough idea of capacitor. So now let's bring in a simple bit of maths here in order to understand the idea of capacitor.